All right, hi, we are Horizontal Filtration. The goal of this sub-team is to design a practical alternative to the stacked rapid sand filter. All right, so as I just mentioned, we want to design a filter better than what we previously have in other plants. What we hope to accomplish is having less volume than the traditional filter, more auric ability, so it can fold and pack better. It'll be easier to build for plant workers, and it'll just be a simpler filter just in case someone needs to dismantle it or something like that.
So the way this filter works is, as you can see in the image, there's water flows in from one side and it flows down an angled plate into a column of sand, and then it goes through the column of sand. It gets all the contaminants and particles get filtered out, and then it flows out the other side. And what keeps the sand in but enables the water to flow through is two vertical plates, which have horizontal shelves, angled shelves in them. So water flows across the shelves, but they're angled so they prevent the sand from getting carried out with the water. And then clean water flows out the other side. That's called forward filtration. That's how the plant normally operates, but after it's been running for a while, contaminant particles start to build up in the bed of sand, and this creates head loss and doesn't let the filter work. So we have what's called the backwash stage, which is filter cleaning. So when this happens, the angled plates at the very sides of the filter pull up, so they block the entrance and exit shelves and the angled shelves. And then water can only flow in through one slit at the bottom of one of those plates. And water flows out through a siphon at the top of the filter. And now, because the vertical area of the filter is a lot larger than the horizontal area of the filter, with the same flow rate, the water flows at a much faster velocity during backwash. So this causes the sand bed to actually fluidize, and the contaminant particles are lighter than the sand. So they rise to the top and get carried out with the water while the sand stays in the filter.
So last semester what we worked on was kind of testing the whole slanted shells aspect of the design. So we based the experimental apparatus on the first team's experimental apparatus, where it consists of a vertical pipe and then an angle pipe. And this angle pipe is meant to simulate the function of the angled shelves. So we ran the experiment where we filled the apparatus with sand and then pumped water through the bottom as the inlet, and then sucked water out of the angled pipe as the outlet. And while it did show promising results, we did have some problems with issues of air bubbles causing the entire sand bed to rise. But when there are times when there are not as many air bubbles, there did not seem to be as much sand rising up the angled shelves. So this indicated that this could possibly be a feasible design. However, we wanted to test better with a more geometrically accurate apparatus, with one that consisted of more flat shells that is more similar to the actual horizontal filtration design, as we thought that this flat surface might cause the water to behave differently as opposed to the curved surface of the pipe.
So one of our major projects this semester was to do a similar experiment, like Nicole said, testing the feasibility of the angled shelf design, but with a flat-bottomed box. So the water's flowing through a wide rectangular slit instead of through a small pipe. And so we designed a box, and you can see the image on the left was our actual apparatus, and the image on the right was our CAD design of the apparatus. So our initial design was water flows in through an inlet pipe on one side of the box, and then it flows through a bed of sand up two angled shelves and then out through two outlet pipes. And so we fabricated this design using a box that was found in the lab that was approximately the size we needed, and then we welded two angled shelves on and welded the outlet pipes on, and then we connected this to a peristaltic pump. So our experimental procedure was to, as I just described, we connected the box to a peristaltic pump. We needed to control the outlet velocity because that's from previous teams' experiments. They discovered that the outlet velocity is what really controls the level of sand rise. So we connected the outlet pipe to the pump and connected the inlet pipe to a water source, and we tested it with increasing flow rates to try to find the failure velocity at which sand would fluidize, and if the sand would then start rising up the pipe. And in the end, we did alter our design somewhat. Instead of having inlet, a water source, and the outlet pipe connecting to just letting the water flow out, we filled the whole apparatus with water, connected it to the pump, and just had the water recirculate. And we tested this, and the results were that the apparatus, in theory, was working well. We did not see sand rising up the shelves, which was the result we were hoping for. However, we discovered that we weren't getting the flow rate that was actually flowing through the shelves and out of the box was not the flow rate that we had measured on the pump, because water fabrication errors, issues with welding at the seams of the shelves and the pipes were causing water to leak between them and leak out of the box. So the water was actually moving at a slower rate that we couldn't measure.
So once we realized this, we had two options to proceed. One of them was being that we would have to completely refabricate the box, where we would weld together 5 pieces of PVC and then add on the shelves to make the apparatus. However, there's an issue of this would take a lot of time, and there would also be the issue of making sure that the apparatus is actually watertight. So we opted to consider 3D printing instead. So with 3D printing, we thought this would be better because it would be more easy to actually alter design. Even after printing, you could just easily alter the CAD and then just reprint the design. Overall, we thought it would just be easier to ensure water tightness of the apparatus. So first we came up with this 3D printed design, where it's very similar to the original apparatus, but it's kind of based off the original actual design that the first team actually fabricated, as seen on the pictures on the right. So we actually scaled this down from a 1:2 ratio, and we thought the scaling it down wouldn't have too much of an effect because overall the dimensions are still the same. So we thought that the behavior of the water and sand would still be the same. For this design, the main changes from the originally fabricated apparatus is just that both sides now have a slit, so both the inlet and outlet would have a uniform flow. Otherwise, the shells are now detachable. We made them detachable because we thought there would be some issues with the shells drooping as we 3D printed them. So the shells will be printed separately, and on one side of the walls there's a hook where the shells will sit on. However, because these are detachable, there's also an issue of if we use this apparatus to test backwash, as water is pumped up through the apparatus, there might be an issue of the shells being lifted up in the process. So originally we wanted to print that first design through Cornell's Rapid Prototype Lab. However, because they're very backed up and the only printer available that could print apparatus of our size would not be available until a couple weeks later, so we opted to consider Hollister's machine shop, where they have a 3D printer, but it prints on a much smaller scale. So we had to either scale scale the apparatus down, or just cut it in half. So we decided to just cut the apparatus in half, where the two sides would fit together in a lock and key mechanism. Beyond that, the only change is that the shells are not detachable from the actual apparatus, as the potential of the shells drooping is not as much of a concern on a smaller scale like this.
All right, so we actually also were able to test the backwash stage this term, and we used an apparatus very similar to the one used last term with the two pipes welded together. What really made this a backwash stage was that we plugged the angled shelf outlet, and we've used a much higher flow rate. We know that plants use a velocity of 11 millimeters per second, and using that and our area of the straight pipe, we were able to calculate a flow rate of approximately 5.4 milliliters per second. We put this into Procoda and use that for the pump. And our goal was to hopefully have the sand fluidize and not let it come out the angled pipe. All right, so our results were very promising actually. As you can see from the video, the sand successfully fluidized and moved up and down the straightened pipe without moving into the angled pipe. So that means that it wouldn't overflow if we were to actually run this with a filter. And it shows promising results for what the horizontal filter can actually do. So moving forward, we have several future tasks, specifically with the 3D printed filter. We hope to finalize the design, and specifically we want to add potential for a backwash stage testing as well. So once we finish that up, we will print it, and then from there, hopefully we can test both the filter and the backwashing stage next term. Thank you. That's all we have. If you have any questions, you can contact us, our net IDs are below.